Alfred Wegener was the one who first proposed the idea of continental drift. He was a climatologist and geophysicist from Germany. In 1912, he published a book called The Origin of Continents and Oceans. He proposed the idea of Pangaea. The evidence he used to support the theory was the continental puzzle, where he used shorelines to show how continents fit. He used fossils by showing how fossils of the same species were found on different continents and couldn't have crossed oceans. For example, the Glossopteris, which is a fern that was found on different land masses, and the Metasaurus, which is an animal found on both sides of the South Atlantic and nowhere else. Wegener also used rock types to support his theory by pointing out how the same type of mountains were found on different continents across the ocean and how he found similar scratches on them that showed that ice moved into what is now oceans. He pointed out that it is very rare for glaciers to move across oceans. Wegener's explanation for continental movement consisted of the pull of the moon on continents, or tidal energy, and how the continents uplift mountains by plowing through oceans. Harry Hess helped support this theory by doing extensive research about the ocean floor in the 1950s. He proposed the theory of seafloor spreading. Hess researched how the Earth's crust had been moving apart. In 1962, Hess published a book called History of Oceans Basins.
Vine and Matthews also helped support Wegener's theory. They were British geologists who found alternating stripes of magnetic field polarity in bedrock in the ocean. This is also supporting evidence to seafloor spreading. Vine and Matthews cited paleomagnetism, which is when magnetic rocks cool and show which direction the North and South poles were originally in. This plays a role in plate tectonics because paleomagnetism reverses polarity, which moves the crust. There are three types of plate boundaries: divergent, convergent, and transform plate boundaries. A divergent plate boundary is when two plates move apart. They are also called spreading centers. Within this boundary, there is the oceanic ridge and rift valley. An oceanic ridge is when the seafloor is elevated on a well-developed divergent boundary, which forms an oceanic ridge. A rift valley is a deep faulted structure that is found along the axis of a segment. A convergent plate boundary is when two plates move together. There is ocean to ocean, ocean to continent, and continent to continent. Because ocean to ocean causes volcanic activity on the ocean floor, because when the plates come together, one of them sinks under the other. Ocean to continent also causes volcanic activity, but on the continental plate. This happens when the oceanic plate sinks under the continental plate. Continent to continent is when the lesser of the two plates sinks under the other, which causes volcanic activity on the margin of the continent. A transform plate boundary is when the plates grind past each other without hurting the lithosphere, which contains the crust and upper mantle.
The causes of plate motion are mantle convection and mantle plumes. Mantle plumes are the hot masses of rock and present themselves as volcanoes or hotspots. Mantle convection is the pushing and pulling of plates, which causes volcanic activity. Plate tectonics occur in the Earth's crust as 7 main plates: the African plate, South American plate, North American plate, Eurasian plate, Australian Indian plate, Madagascar plate, and the Antarctic plate. These plates are all shown in the image above. Plate tectonics show us geological structures like folds, a bend in the rock layer, and faults, a crack or break in a rock layer. They also show us volcanoes. The two main types of volcanoes are basaltic and andesite. Plate tectonics show themselves in earthquakes as shallow focus, which means that there's 40 miles or less, and deep focus, which means that there's 40 miles or more away. Plate tectonics show us mountains, rift valleys, and oceanic ridges, which are deep faulted structures along the axes of segments and oceanic ridges. The oceanic crust gets colder and denser as it ages, making it disperse into the mid-ocean ridges and sink into the upper mantle. It's like a natural recycling system. Continental crust is lighter, which is why it's much older than the ocean floor.
In conclusion, thanks to the studies of Alfred Wegener, Harry Hess, and Vine and Matthews, we now have a better understanding of our Earth and how it moves.